Hey, so welcome back, and this is another daily code problem. So today it was actually another dynamic programming one, so let's go ahead and get to it. So this one is called maximum value of k coins from piles, and it's a hard question from Google. So it's not that popular, but I think it's a really good problem. And so we're going to use a one-dimensional dynamic programming solution for this. So now, I thought it came fairly intuitive for me. Yesterday's problem was also dynamic programming one, so I kind of went into this once I saw the hard problem. That's probably like a dynamic programming one, and I usually do much better with the one-dimensional ones than the two-dimensional. So yeah, but to explain the problem, basically you're just given n piles here, and each list within this 2D array is a single pile. So there's two piles here. This is the first one, and this is the second one. And then you're also given a k value here, which represents basically the number of choices that you can make. And so what you want to do is you want to maximize this. You want a maximum total value here. And each of these, I guess, layers within each pile is a value that's associated with it. So this is worth 1, this is worth 100. You can think of it as dollars. So like there's $1 here, $103. Then in this second pile, there's $7 on the top, then 8, then 9. Okay, and so you can pick from these piles using k kind of picks or choices here, but you have to start from the top. So you could say, okay, I want to grab this one, and then once I pick this one off the pile, I have a worth of 1. And then I can pick this second one from this pile, which gives us 101. Okay, and that's actually the answer for this, is no matter, there's only 3 different variations. You can either pick 1 from each pile, 2 from the right pile, or 2 from the left. And naturally, these 2 here equate to the highest value, which is 101. And so that's like the solution for that. Then for this pile, here you can see that there's multiple piles, but they all just have like 100 at the top unless you pick from this one. And so you're given 7 choices. So in this case, what you do is you just grab 100 from each of these piles, 1, 2, 3, 4, 5, 6. And then you just go ahead and you just keep picking from, I think there's actually 7. I don't actually get why you can get 706. So 100, 200, 300, 400, 500, 600. Is it that? So in this case, I actually didn't read this one. What you do is the highest way you can get for this is, although you could pick from each of these piles here, these 6 piles, because you only have 7 choices, picking these 6 100s and then 1 from here, it would only give you 601, 601. But since this here has a depth of 7, then you just pick 1, 1, 1, 1, 1, 6 times, which gives you 6. But then you can grab this 700 to get you 706. So that's an interesting one. So yeah, so basically for this, we're going to do a top-down solution, and we're going to use like memoization for it, or like caching on the recursive layer. And let's create our DP array. And to do this, what we're going to do, and I felt this was the easiest one when I was looking at other people's variations of the solutions, is you can actually accumulate, there's an accumulate function, a list here. So let's go ahead and build that list, and I'll show you what this is going to look like in a second. So for every pile in our piles, we're going to accumulate that pile. So if I just print out this DP array, so print DP, is for this first example, if we take a peek at it, what this does is you're given 1, and then you just keep adding to it. So then 1, then 101, then 104. And so it just, like, when you call this accumulate function, it takes like the running sum, I think is the best way of explaining it. And so then the second pile, it goes 7, then 7 plus 8 is 15, then 7 plus 8 plus 9 is 24. So it's just an easy way so that as you're drilling down on this pile, you can keep track of the running sum. So at this layer, you'll have $1, but say if you pick the second layer, then you'll have 101. So rather than having to maintain it like with a variable summing it all, you can just keep track of, okay, if I'm at the second layer on this particular pile, we know the worth and it's that, okay? And so let's go ahead and create our recursive function. We'll call this calc maybe, and we'll return this at the end. And we'll pass it two different things. One of them will be the number of choices that we have remaining, and we just initially set that to k. And then the other one will be I, and that's just going to represent which pile we're looking at. Okay, so initially we're looking at the first pile, so we'll pass in 0 here. Okay, so let's just put an I to represent, okay, I'll put a comment here, I equals the ith pile, and then k is number of choices remaining. Awesome. And so to do that, let's go ahead and we'll say if we need a base case here, okay, and that's going to be if we either have no choices left, so if no choices remaining, and that's just basically k is 0, or the other base case is or if there's no piles left. So let's say I is like 3 here. Since there's only 2 piles, we can't consider any other pile. So or if I like is greater than the number of piles. So that could be the case where since there's only 6 different coins in this pile, and let's say that we were given like k equals 1,000 choices. Naturally, there's a limit. We can only grab from these 2 piles and all 6 coins. And so then we'll be looking for a third pile, and we want to say, okay, there's no more piles. Although you have 5,000 or 10,000, a huge number of choices, you're limited to the number of piles that you can get for this output. Okay, so that's the base case. So if k is 0 or if our I is greater than the number of piles, which we could say is greater than or equal to the length of our piles array. Okay, and so that's good. And so from there, we want to consider 2 different cases. The first one is we can say, okay, case 1 is if we skip this current pile, skip pile. And then the second case is if we grab from current pile. Right, and so to better visualize that, let's just say that, okay, initially we start with k choices, so k is 2, and initially we're looking at pile 0 here. We could either pick from this pile, say grab this first one and continue down if we want, or we can say, okay, why don't we check the second pile instead. So that's case 1, is we just skip this current pile, we look at the next one. All right, and so to do that, it's pretty simple. We just want to call our recursive function, and we want to increment the pile number, right? Because we're initially looking at pile 0. We want to say we want to look at the next pile. And then we just keep the number of choices. So see, at this point we have 2 choices. If we skip to the next pile, we keep the number of choices that we had at this previous pile, okay? And so because at the end of this function, we want to return like our output or our answer, that's like the maximization, you just want to return whatever result that you might get from skipping this pile. And so then we want to handle this second case where we grab from the current pile. And so to do that, we want to be able to say, okay, we want to consider the entire depth of this pile. So because this pile has multiple layers of coins, we want to iterate through each layer. So for j in the range of the length of the pile at this index. So I believe that these piles can have varying heights to them. Like one pile could have 7 coins, while the other pile could have 2 coins. And you saw that here, where this pile had a way bigger depth than these other ones with only have one coin on each pile. So at this particular pile, we want to iterate through every layer. Okay, but then we want to limit this to the minimum between the length of that pile and the number of choices that we can make. So say the pile has a length of like 7 in this case, but then let's say k was equal to 2 at this point. So we pass in k equals 2, but then the height of this pile is like much longer. We're limited to either the height of the pile or the number of choices we have. So let's just take the minimum of those two. Great. And so from there, let's go ahead and iterate through here. And so we'll want to update our answer or our output here as what? We want to take the maximum, because it's a maximization problem, of either what we currently have so far, what we've currently calculated by either skipping the pile or through a previous iteration in this for loop, and if we actually grab from this current pile. So that would be the, let's see, I'm trying to think here. If we go ahead and grab the coin from this current pile. And so that would look like this here. So say if at this current pile, we want to grab that coin, so that would be at this inner dynamic programming kind of DP array here. We have set our accumulation of what these are worth. And so say we're at the second layer, we want to grab this value. And so we would just do at I, at j here. Right, and so that just symbolizes this 100 here. All right, and so from there, what we want to do is call our recursive function, our calc, and we want to decrement the number of choices because we just made a choice. We said, okay, we want to grab this value at the jth depth in our current pile. And so we would want to pass in k minus 1, but then also we want to consider looking at the next pile. So we could either continue on with this for loop, right? Because this for loop keeps iterating and keeps going down the depth of this, or we can say, okay, we can either keep going down this pile, which represents this for loop, or at any point we could say grab 100 and go to the next pile. And that's what this indicates, is grab 100 and go to the next pile. So from there, what we want to do is we say k minus 1, but then let's go to the next pile, which once again, you just do I plus 1 to increment to the ith plus 1 pile. Okay, so let's go ahead and run that. Oh, I just got a wrong thing here. I plus 1, comma k. Oh, here, I just forgot to put in our base case. So in that case, we just return 0 and we just kind of keep propagating up that recursive tree. And pile is not defined because it's called piles. Oh, there's something wrong here. For a list, accumulate pile. If we're iterating through here. I think that's fine. If k is equal to 0, there are no choices left. Then I is greater than or equal to the length of our piles. Skip to the next pile, but we keep k. And I'll just move you over here. Initially we have k, go down to 0, and the answer is the maximum of that. Oh, okay. So I think that makes sense. So what we're doing here is we say k minus 1, and k is the number of choices that's remaining. But because this is a for loop, and each time we're iterating down this stack, we might have iteratively gone down this stack like 4 times or 3 times in this case. And so we didn't just do k minus 1. We might have done like 2 hops. And so we needed to count for the number of hops we've done, and that's indicated by j. So j means we've iterated down the pile twice. And so really we want to do k minus j, because say you're given 2 choices and you iterated down twice, then you want to like account for each iteration. So if you run that, okay, I think I remember this. And so just minus 1. Yeah, and so that's just the edge case of the number of zeros that we have. So because I think this starts at 0, initially you'd be doing like k minus 0. And so you have to do k minus j minus 1 because the first iteration is j is only at index 0. So because you're dealing with the indices, you have to do minus 1. Because on the second iteration, you'll be at j equals 1, but you want to subtract 2. So let's go ahead and submit this. Just taking a little bit. Oh, I think we're going to get a TLE, so we have to add a caching here. So let's add a cache. Yeah. There we go. Okay, awesome. So it's great. It performs really well. And yeah, I would say it's fairly intuitive. I think my explanation went fairly good. Like basically there's 3 different cases. The base case is that, okay, say you have no more choices, so k is equal to 0, then let's just return 0 because you can't go any further. And you kind of propagate up that recursive tree. If I is greater than or equal to 1, that means that, okay, you're trying to pick from a third pile, but there isn't a third pile, so just stop there and don't add anything. Then you can say, okay, we can either skip this pile and just immediately go to the next one, don't even use any of these coins here, or you can grab from the current pile, and at any point you can say, okay, I can either grab from this pile at this point and hop to the next one, or I can kind of keep going down this pile, and you just take whatever the maximum of those 2 different decision trees as you're recursively following each path. Okay, so at every iteration you can say, I can either grab this coin and hop to the next pile, or I can go down to the next layer. Okay, and that's the solution. So yeah, I hope that helped, and good luck with the rest of your algorithms. Thanks for watching.